Welcome back to the deep dive. I'm betting you're the kind of person who loves getting to the heart of complex topics. Really understanding the ins and outs without wading through pages and pages of technical jargon. Well, today we're diving headfirst into the world of federated learning and a fascinating new development called FedNets. You've probably noticed, machine learning is everywhere these days. It's on our phones, in our cars, powering all sorts of smart devices.
It really is. And the traditional way that all these smart devices learn, well, it involves sending all the data they collect back to a central computer, a big server for processing and analysis. But you can kind of see the problem with that right away, can't you? All that personal data all in one place, it creates these huge privacy risks, and it raises all sorts of legal questions, especially with things like GDPR.
Right. It's almost like creating this giant target for hackers, this honeypot of all our sensitive information. So that's where federated learning comes in. At least that's my understanding of it. It lets these devices learn and improve right there on the device itself. The raw data, like your photos or sensor readings, never actually leaves the device.
You've got it. Instead of shipping all that data off to a central location, each device trains its own little model, like a mini brain, using its own data. Then, only the updates to these local models, things like adjustments to the model's internal settings, are sent back to a central server. That server combines all these updates to create a better, more informed global model, which then gets sent back out to the devices. It's a really clever way to let devices learn collaboratively without compromising privacy.
It sounds like a win-win.
Mhm.
But I know there's a catch, right? Something about the data being different across users and devices.
Ah, yes. You've hit on a key challenge in federated learning. The data coming from all these different users and devices is often, well, wildly different. Think about it. How you use your phone is probably totally different from how someone else uses theirs, right?
Definitely.
Yeah. The apps we use, the times we use them, it all creates these unique patterns in our data. And this is what we call non-IID data, short for non-independent and identically distributed. Basically, it means that the data set on each device has its own little quirks, its own statistical flavor.
Okay, I'm starting to get the picture. So my phone might train a model that gets really good at understanding my usage patterns. But if my patterns are completely different from everyone else's, how does that really contribute to creating a global model that's actually useful for everyone?
That's the million-dollar question. You see, in standard federated learning, if each local model is trained on very different data, the updates they send back to that central server can actually start to work against each other, like a tug of war. Instead of the global model getting progressively better, it might end up stuck in this mediocre middle ground, and the whole learning process can take much, much longer. The research paper we're looking at today actually includes a helpful graphic, Figure 1, that shows how these local updates can pull the global model away from the true, optimal solution.
Yikes. It almost sounds like they're undoing each other's progress.
In a way, yeah. So what have researchers been doing to try to solve this problem of having such different data on all these different devices?
Well, they've been trying a bunch of different things. Some of these approaches focus on making the data itself more uniform.
So like trying to even out the playing field a bit. Exactly. One idea is to share a tiny, tiny slice of everyone's data globally, just a little bit, hoping to create some common ground for the models to learn from. Or they use techniques to artificially expand the diversity of the data on each local device.
But wouldn't sharing data, even a little bit, kind of defeat the purpose of federated learning in the first place?
That's the trade-off, right? It's a bit of a tightrope walk. You want to improve the accuracy of the global model, but you don't want to sacrifice the privacy benefits that make federated learning so appealing. The researchers even cite a specific example, I think, is using image data. They found that sharing just 5% of the data improved the overall accuracy, but yeah, it did come at a cost to privacy.
Right. You can't have your cake and eat it too.
Yeah.
So what about trying to tweak the learning process itself instead of messing with the data directly?
Now you're talking. There's been a ton of really cool innovation in that area. Some methods involve giving those local models a bit more freedom to, fine-tune the global model they receive to better suit their own data. Others actually add special non-shared components to the model, kind of like little side compartments where the model can learn individual user patterns. Researchers have even borrowed ideas from fields like multitask learning and knowledge transfer to try to tackle this.
Those sound pretty clever,
Yeah.
but I'm guessing they have limitations too.
Yeah, there's always a trade-off, like in knowledge transfer. Sometimes trying to learn from one source of data can actually make the model worse at understanding another source. It's called negative transfer. And those personalized components we talked about, well, the clients can't really share those with each other, which kind of limits the whole collaborative learning aspect of federated learning.
It's starting to sound like a pretty tricky puzzle to solve.
Oh, it is. And then there's another approach we haven't talked about yet, grouping clients together.
Ah, I think I saw something about that in the research.
Yeah. The idea is to try to identify devices that seem to have similar data characteristics and then train more specialized models within those groups. You could group them based on how well the models are performing locally or even based on the internal settings of the models themselves. But there's a catch. Figuring out how to group these devices, especially when you have a massive number of them out in the real world, that can require a lot of computational power and a ton of communication between the devices and the central server.
Okay, so it sounds like researchers have been trying to crack this non-IID data nut from all different angles. And that brings us to FedNets, the star of the show today. What makes this approach stand out from the crowd?
Here's where things get really interesting. FedNets goes in a totally different direction. It uses something called deep ensemble learning. So remember how in standard federated learning, each device has just one model, and it sends updates to that model. Well, in FedNets, each device has a whole collection of models, a committee, an ensemble of different, smaller, deep learning models. And instead of just sharing tiny tweaks to a single model, they share entire models with each other. These models are designed to be lightweight, of course.
So it's like instead of one brain, each device has a whole team of mini brains working together.
Exactly. And these mini brains, or models, they're initially chosen from a global pool of models that have already been trained a bit and then made smaller and more efficient. The key is to start with a diverse set of these lightweight models. Then each device takes its little team of models and trains them on its own unique data, which could be wildly different from what other devices are seeing.
Okay, that makes sense. But then how does the device make a decision or prediction using this whole committee of models?
Well, when it's time to make a prediction locally, the device consults all the models in its ensemble and combines their opinions. Often it's as simple as taking a majority vote. The thinking is that having multiple perspectives, multiple models weighing in, leads to more accurate and more reliable predictions right there on the device itself.
Okay, I can see how having a bunch of different models could give you a more well-rounded, robust prediction locally. But how does this help with the federated part of things? How does it address the problem of non-IID data across all the different devices?
Ugh, that's the genius part. This is where something called graph embedding theory comes into play. To manage all these different models and figure out which ones are most valuable to share, FedNets treats each deep learning model as a network, or a graph. Think of it like this. The different parts of the model, its layers, are like points on a map. And the connections between these parts, they're like the roads connecting those points. The characteristics of each part of the model, things like the average settings within that layer, those become like features of those points on the map. The paper even has a diagram, figure 3, to help visualize this.
So each model gets its own unique map, kind of like a fingerprint, based on its structure and what it's learned.
You got it. Then, FedNets uses a spiral type of neural network called a multi-layer perceptron, or MLP for short. Think of this MLP as a really sophisticated translator. It takes this complex map of the model and transforms it into a shorter, more manageable code. It's called an embedding. Equations 1 and 2 in the paper describe this process. And this embedding, it captures the essence of each model, kind of like a summary of its learning in this compact little code.
And it can then group those model fingerprints together based on similarity.
Precisely. It uses a technique called affinity propagation to do this. FedNets looks at all these fingerprint embeddings from all the models across all the devices and automatically clusters the models that seem to have learned similar things. It's like finding natural groupings of models that have become experts in different aspects of the data.
So it's like identifying groups of models that have specialized in different areas.
Exactly. Once it's found these clusters of similar models, FedNets selects a few representative models from each cluster. These representatives, they're the ones that get sent back to the central server. And they're chosen based on how big each cluster is and how well the models perform on a small bit of local data that's set aside for validation. The researchers even give a formula for how they choose these representatives in equation 3 of the paper. These chosen models, they're then shared back to the global pool, and they can be sent out to other devices in the next round of training. This way, the global collection of models is constantly evolving, always incorporating new, diverse, and effective models that have been trained on all sorts of different data.
So it's like a multi-stage process, really clever.
Yeah.
What are the biggest advantages that FedNets offers, especially compared to these other approaches we've talked about?
The researchers highlight several key benefits. First, This deep ensemble learning approach, it allows the models on each device to become much, much better at understanding the local data, even if that data is very, very different from the data on other devices. Second, by using those fingerprint embeddings to group similar models together and only sharing a few representatives from each group, it drastically reduces the amount of communication needed between the devices and the server. And it saves a ton of storage space compared to if they were constantly sharing all the full models. And third, this is a big one for privacy. FedNets provides a built-in layer of protection. You see, because clients are sharing entire models, these ensemble members, rather than just tiny updates to a single shared model, it becomes much, much harder for someone to reverse engineer those models and figure out sensitive details about the original training data.
It's kind of like instead of sharing the exact recipe, they're sharing a collection of slightly different finished dishes.
Exactly. It's much harder to work backward and figure out the original ingredients and measurements from the finished product. So how did FedNets actually perform in the real world, or at least in simulations? The researchers put FedNets through its paces using something called the Federated CIFAR 100 dataset. This is a popular benchmark for federated learning because it's specifically designed to mimic that messy, varied, non-IID data you find in real-world situations. They wanted to see how much better FedNets could do compared to just using a standard model called ResNet v2.
Ah, ResNet v2. I think I've heard of that one.
Yeah, it's pretty common architecture. Just to set a baseline, when that ResNet v2 model was trained on the original non-federated version of the CIFAR 100 dataset, it reached an accuracy of about 68%. So that's what they were trying to beat.
Okay, and then they created their initial set of those smaller, more efficient models for the ensembles.
Right. They started with a pool of 500 of these pruned ResNet v2 models. Pruning, it's like carefully snipping away less important connections in the network. You make the model smaller and faster without sacrificing too much performance. These pruned models ended up being about 37% smaller on average. Each one was about 12,295 kilobytes in size. And importantly, the accuracy of these individual models varied quite a bit, ranging from just 0.05% up to 66% on a validation set. That diversity in the initial pool of models is really important for the ensemble to work well.
Got it. So how did FedNets stack up against those more traditional federated learning approaches like FedAV and FedYogi when faced with this varied data?
The results were pretty impressive. When they simulated a scenario with just 2 clients, FedNets achieved amazing accuracies, 93% on one client and 86% on the other. Meanwhile, FedAV only managed 56% and 14%, and FedYogi struggled even more at 1% and 60%. You can see these results in Figure 5 of the paper. And the pattern continued as they added more clients to the simulation. With 5 clients, shown in Figure 6, and then with 10 clients, shown in Figure 7, FedNets consistently outperformed both FedAV and FedYogi, often by a significant margin. The paper even points out that FedNets showed accuracy improvements of 63% and 92% against FedAV and FedYogi, respectively, on the Federated CIFAR 100 dataset.
Wow, those are some serious gains in accuracy. But let's talk about the practical side of things. Running a whole bunch of models on each device, that sounds pretty computationally expensive, especially on those less powerful IoT devices that are often at the heart of federated learning.
You're right. That computational cost is a major consideration. The researchers did analyze how well these ensembles performed on simulated virtual clients. And what they found, you can see it in Table 2 of the paper, is that the time it took for each device to train its local ensemble, that was the biggest bottleneck. And as you might expect, the more clients they simulated, the longer that training time became. For example, with 10 clients running on regular computer processors, CPU nodes, a single round of federated learning took almost 12 minutes. However, they did point out that the time it took for the ensemble to make a prediction once it was trained, what we call the inference time, that was generally pretty reasonable for most applications.
So maybe not the best fit for something that needs lightning-fast responses on a low-power device that only has a simple CPU.
Yeah, that's a good takeaway. But here's the good news. They also showed that FedNets is actually quite good at reducing the number of models in the ensemble on each device over time as the learning progresses. Table 3 in the paper shows that they were able to cut the ensemble size in half after just 4 rounds of training, which is great for conserving those precious resources on those smaller devices.
Okay, that makes sense. And what about that privacy aspect they emphasized? How does sharing these whole model ensembles help to protect privacy?
The privacy protection comes from a couple of clever mechanisms. First, each device only shares a portion of the models from its local ensemble. Let's say a device has, for example, 10 models in its ensemble. It might only share 5 of them. The ratio of models shared versus models kept private, that acts as a kind of control knob for privacy. The fewer models you share, the more privacy you potentially maintain. Second, the fact that the ensemble itself is diverse, that adds another layer of protection. Even if a few models are shared, if the whole ensemble is very varied, it becomes much harder for someone to reconstruct those models and figure out specific sensitive details about the data that was used to train them. They observed in their experiments, you can see it in Table 4, that when they started with an ensemble size of 10 models per client, they tended to share a lot of them initially, on average like 9.6 models. But they also point out that they could easily adjust that sharing rate, what they call the parameter, to fine-tune the balance between achieving high accuracy and maintaining strong privacy.
So it's like a trade-off slider. They can adjust it to find that sweet spot.
Precisely.
So it sounds like FedNets offers a pretty compelling compromise, doesn't it? You get better accuracy in these tricky situations where the data is all over the map, and you get a built-in mechanism for protecting privacy. The only real downside seems to be that it can take a bit longer for each round of training, especially on those less powerful devices.
That's a great summary. The researchers themselves acknowledged that those longer learning times, especially on devices without specialized AI hardware, might make FedNets less suitable for applications that require ultra-fast responses. Things that need to happen in real time. They even suggest in the paper that future work could look into using even more efficient model architectures, things like MobileNet, which are specifically designed to run well on devices with less processing power.
So taking a step back and looking at the big picture, what's the key takeaway you think our listeners should walk away with from this deep dive into FedNets?
I think the main thing to remember is that FedNets represents a really promising leap forward for federated learning. It tackles head-on this huge challenge of dealing with diverse and different data across many devices, and it does it while achieving really impressive gains in accuracy. And on top of that, it provides a solid level of privacy protection through this innovative way of using ensemble learning.
It's definitely a development worth keeping an eye on as we see more and more devices coming online and generating their own unique data. What are the researchers planning to explore next with FedNets?
They have some exciting plans lined up. First, they want to test FedNets on even more complex and varied datasets to see how it performs under pressure. They're also interested in experimenting with more advanced neural network architectures within their ensemble framework. And they want to really dig deep into optimizing all the different settings and parameters of FedNets, fine-tuning the engine to see if they can squeeze out even better performance and maybe even improve that privacy accuracy trade-off even further.
It's a fascinating stuff. It really makes you wonder how these kinds of innovations will shape the future of machine learning and data privacy as our world becomes more and more connected. Thanks so much for taking this deep dive with me. It's been really enlightening.
The pleasure was all mine. It leaves you thinking, doesn't it?
Yeah.
As the number of connected devices keeps skyrocketing, how will advancements like FedNets fundamentally change the way we approach machine learning and protect our personal information in this ever-expanding world of the Internet of Things? It's a big question, and the answers are going to be really interesting to watch unfold.